No. Sir, log for 5 and 6. Week 5 and 6.
Which one?
So week 5 and 6.
Week 5 and 6. Okay, it is not available.
No,
Okay,
sir.
okay, fine. It should be there, right? Okay, I will. Maybe the mail is sent out this week. Okay, maybe I will check. Okay, okay then shall you start then today's session?
Yes, sir.
So yeah, so to adding to this, what you have to do is you have to just uh, go through the materials or whatever is available there, and you just go through the concepts. Don't by heart the formulas, anything. You just go through the concepts properly, see how the steps are, what are the steps to follow to solve that question. Okay, and then try the questions. Maybe it will help you, because uh, if the path to solve a question is clear to you, right, then it is not problematic to find the answer. So there is only one chance to get it wrong is if you do calculation mistake. Otherwise you don't do the mistakes if your thinking is clear. So whenever you see the problem, you should have in your mind that what is if this, okay, this is the problem, what steps to be followed to solve this problem. If it is clear in your mind, I don't think it will like end up in losing the marks or maybe making any question wrong.
Okay, sir.
Okay.
Yeah.
Okay.
Okay.
We'll see.
Thank
Like yeah. Meta.
Yes, sir.
No, not for you. So
Okay, sir.
okay. So where to start? I don't want
From slide 1. Which
slide
you are
1.
presenting.
The Bayesian estimation, sir.
Yeah, I know, but
I have not understood anything in that slide, sir, in the lecture.
in the lecture you don't understand. Have you gone through lectures?
No, sir. You are just showing the slide 1, sir.
No,
अभी
I
दिखा रहे थे
know.
आप.
I know, but what I'm saying is, from where to where should I start? Should I start from the beginning or should I start from?
Please start from beginning, sir. Please.
Okay.
Yeah.
Just give a minute.
Sir, is week 11 is the last lecture, sir? Last week, course-based content.
So there's so much noise from, I think, traffic. So
Okay, so we'll start it from here. Okay, until now, have you understood? Like, okay, maybe what I'll do is, it's clearly visible, right? This thing.
yes, sir.
Yes, sir.
Okay, just give me. I think I'll open it in the PDF so that I'll be able to write it there. Okay, just a minute. Hello. Hello. Okay.
Yes, sir.
So
Yes.
this is visible, right?
No, sir. Screen is not visible.
1 minute. I haven't shared the screen. Okay.
So now it is visible.
Now it is
Yeah,
it
yeah.
is visible, sir.
Yes. Okay, so until now, what you have studied is maybe in week 9 you studied about method of moments and maximum likelihood method to estimate the parameters, right? So this will be the standard setup. I think I have taken one session where I have mentioned about like how this x1, x2 to xn and how they are belonging to some distribution. I think I have mentioned it in like maybe in broader, like not broader way, I think in depth I have told you. But okay.
Yes, in week 7 you had discussed it.
Yeah, right. Somewhere I
Yeah.
know that where I discussed about like what is x1, x2, xn and why they are variables and something about that. If I remember it correctly. Okay, so now this is the standard setup where x1, x2 to xn will belongs to some IID x distribution. Okay, and it will have a parameter, right? If suppose if this x1, x2, xn belongs to IID x and x is Bernoulli P. So what is the parameter here? It is
P.
right? So in previous problems, what we had is before parameter estimation, what we had is we know that P, right? Maybe it is 0.5, maybe it is 0.45 if it is a biased scenario or something like that. But in real case, if you don't know what is that parameter, how to find that parameter, right? That for that we need to have like 2-3 methods to solve this, right? So there were I think we have already studied about method of moments and maximum likelihood, where what happened is this parameter theta or maybe that parameter P in case of Bernoulli, we treat this as constant. What does that mean? We are saying that even if you are taking so many samples from that distribution, this parameter was unchanged, right? It was constant. So what I wanted to say is, suppose you have taken, suppose I said x1, x2 to xn belongs to some IID, let's say it's Bernoulli.
IID samples.
Right? Okay, 1 minute. Thickness is too much. Fine. IID.
So you mean when you're changing the samples, the value of theta is independent of that?
Yes, correct. So this does not depend on these samples, right? Or it is not varying. Yeah. So in case of this method of moments and maximum likelihood, where we are saying that this P is constant, irrespective of whenever, like how many times you are taking the samples from that distribution. Understand my point? Like for example, if I take this was my sample. Let's say if it is x1 to x5, okay. Similarly, this is first sample taken. Then for the second sample, suppose this like this. But all of these samples, how many times if I'm taking those samples, this P was treated as constant. So this parameter P, when I wanted to estimate this parameter P, it was treated as constant. And this approach is used in these two methods, which is method of moments and maximum likelihood. And I think these two are fairly simple methods, not much difficult about it. Similarly, Bayesian estimator is also not difficult. But these are the methods where there is a certain framework, right? So for method of moments, you know what are the steps to follow to find the answer. Similarly, for maximum likelihood, you know what are the steps to follow to find the final estimate. Same thing will happen for Bayesian estimator. You already know that how to okay, this is directly this is belongs to, or this is directly proportional to something, and if you follow certain steps, you will find that estimator. Okay, so it is just that you might get confused with 3 methods. So what you have to do is you have to make clear notes on all 3 methods and just practice it more and more times on the same problem, because if you are given any problem, you can actually solve it by using method of moments and maximum likelihood method. Similar problem can be solved by Bayesian estimator also, but only thing is you need to know the prior. So if you have one problem, try to solve it by 3 methods. I think it will help you better understanding the difference between 3 methods. Okay, so I think
yes,
yeah. So I think until now it's fine. I think this setup, method of moments and maximum likelihood is fine. But what one thing you have studied in maximum likelihood method is how to find a likelihood, right? So what is likelihood?
So the probability of occurring of that event, which is taken as sample, right?
Right. Okay. So so for example, for this method, how to find the likelihood? So for this sample, if I wanted to find okay, this belongs to, let's say, IID Bernoulli some P. In that case, what should be the likelihood for this sample?
P into 1 plus 0.
P into
P into
1 minus p to the power 4 into.
yes.
okay. Is it correct or is it wrong?
No, the P
raised
into
to
1
4
raised
or
to
1
4.
minus
Wrong,
p
sir.
raised to p to the power 4
1
into 1
minus
minus
p
p
raised to
to the power 1.
It should be a likelihood, right?
Yeah, yes.
Right. So everybody understood this. So why is p to the power 4? Because see, 1, 2, 3, 4 times it's coming, right? So I need to multiply that many times. It's a product of the probabilities.
Yes,
right?
a binomial distribution it is.
I want to ask one thing here, sir.
Yeah.
The question is, we are taking p to the power 4 because we are assuming 1 to be success and 0 to be failure, right?
Correct.
If we take 0 to be success and 1 to be failure, then
Why?
it would be
No. See, the thing is, if I say IID Bernoulli X, right? So IID Bernoulli and with P. So when I am saying this P, then that belongs to what? It will always be this case, right? 0, 1. If I wanted to
Yes,
say,
sir.
then what I have to do is I have to write it like this: 1 minus P. Right? Something is like, because we know that
The probability is always given success, right?
success, right? So this is already for success, right?
No, sir. I am adding further question is that if we consider 0 to be a success and 1 to be a failure,
Then what you have to do? So if if you wanted to do this 0 to be success and 1 to be failure, then just change this to 1 minus P, right? Because that P is given by default for the value 1, which is taken by a random variable.
okay, sir.
Right?
Okay.
So if you do that, you will get a same answer. Otherwise, you will get the wrong, different answer, and it will end up losing the mark, right? So, and most probably our convention is 0 is for failure and 1 is for success, right? Okay. Okay. So there is third approach, which is Bayesian approach, where we treat this parameter theta as a random variable with a known distribution. So that means this theta is not now constant, right? It is also changing, and it is changing with certain distribution. Okay, it will be a known distribution. So we'll think about, like, we will see what kind of distribution is there, or okay, depending on the distribution, we can actually categorize this Bayesian estimators into or these priors into 3 different categories. We'll see that.
Sir, like when we are saying theta, like for till now, what I understand is we were trying to approximate the distribution of X, right, from the samples, basically.
Approximate right, distribution of X. I don't understand. Like
we were trying to calculate parameters of for the distribution of X.
Yeah.
Right? And for that we were taking samples from the population.
Correct.
Right.
Correct.
And now so it did make sense to assume that X will have a like fixed parameter because its distribution will be fixed, right? So I was taking different samples and I was trying to find that fixed parameter.
Okay.
Now, assuming that parameter itself is variable, it is changing with respect to samples. That does not make sense. Like
why? Why it is not
suppose I was trying to approximate, like, let's say X is the height of a person, right? Then what I was doing is I was taking sample of 1,000 people, again 1,000 people, again 1,000 people, so that I can maybe I know that it is normally distributed, so that I can find those parameters, right? Now what we are saying is that those parameters of height changes with samples. That's what we are saying, right?
See, okay, one more thing. So here we are not sure about that parameter itself, right? Because so you are taking the height of a person, let's say height of a person in India, for example, right? So that is my population, because the capital X is what? it belongs to a distribution of a population, correct? So in
Yes, sir.
case if I I just wanted to know what is the height of a person in India, or maybe let's say male only. We are not considering the female, only let's say male. So now in that case, I know that it is normally distributed, right? You know that is normally distributed. The only thing I don't know is what the parameters of that normal distribution. What are
Yes,
those
sir.
parameters? The one is mu means what mean, and sigma square, that means variance, right? So I don't know these parameters. So there will be two approaches to find these parameters. So one thing is you're saying that I'm taking the samples of, let's say, 1,000 people, right? So 1,000 male, you have taken the sample, you have calculated some parameter from that, or you have calculated some distribution from that, for example, right? You will get some mean and you'll get some sigma square, right? Again, in the next 1,000, you will get something else, right? But what I'm saying, in one approach, we are assuming that okay, that parameters mu and sigma square are constant. Okay. Anyway, see, if I take the heights of all the persons in the population, I'll definitely get one value for mean and one value for sigma square, right? And that will be the correct value. That will be the true
That will
value.
be population.
Right?
Yeah,
But
yeah.
it is not possible in that scenario. How many people you are going to see? It will be like, let's say, we'll think about like 70, you know, how many people, like we have 1.5 billion people, something around like that, right? So if you take the half of the population, it will be very difficult for you to find the exact parameters for that normal distribution, correct? So now there will be two ways that let's say that parameter, when I take the samples, so for example, okay, I'll tell you one scenario. Suppose
Sir,
I have,
sir, are you saying it like suppose I took a sample of 1,000 people
yeah,
and I calculated parameter, maybe let's say using
yeah,
method
let's
of
say
moments,
yeah,
right?
some
So I
mu
did
and
not
sigma
consider
square,
other
yes.
samples. I did not consider other samples because I'm assuming that it is same for all the samples.
Yes, because see, if you take differently, you will get some values of mu one. Let's say this is mu one, sigma one square. It is mu two, sigma two square, right? So you will get actually different values, right? So so there will be 2-3 ways. For example, if I say, let's say, okay, again 1,000 student, 1,000 people, then again 1,000 men, you will get different values of this, right? Sigma square. So now there is one way that okay, you can think by using these two methods, method of moments and maximum likelihood, that okay, if I take one sample and from that I told that okay, that parameter was constant and it should be equal to this, right? Mu one and sigma one square. I'm
So
not
in those two methods, we are not caring about other samples.
Yeah, so or maybe you can take other sample, you will get different value anyway, right? But still you are
But
saying
we are
that
just taking one sample, just at least.
one only, right, at a time, and you are saying that okay, this should be the value, and I'm assuming that okay, that should be the value for the population, correct? But now if I know prior, like so now if I have some information, right? Okay, suppose with this method you said that with method of moments and maximum likelihood, that okay, what is the average Indian male height is, let's say 150 centimeter or maybe 155 centimeter, right? Okay, with this methods, if I got this value, okay, and I said that okay, this is correct, but we have a lot of data, right? We have prior data for the past some years, maybe when we started with census or something, like let's say we have some data, and with that information, if I know that this height will be around like 150 centimeter, and it is having some 1 meter, I'll just come to you also. So 155 centimeter, and okay, I'm taking this one parameter here. So suppose this is 157 centimeter from my prior information, but it is definitely possible that it might change, right? It might be varying, but okay, one thing is sure, that that value should be very close to this value, right?
157 close
centimeter. With this my prior information, if I try to, now this is, let's say, if I have some information, and with that information, if I'm trying to estimate a parameter, so that will be very close to the we can say that will be very close to what the exact value of a population, or exact value for the parameter of a population. Okay, without information, it might end up with this method of moments and maximum likelihood, you might get some because it depends on the
Sample itself.
only the sample, right? Only the sample. You might
Sir, 1
end up-
minute.
We are just adding one more piece of information to it, right?
So you get this parameter, but that is not, that might not be a correct one, right? But if you have some prior information, you actually end up with very close to whatever the exact parameter will be.
So this
Right.
157 centimeter is what you are talking about, non-distribution.
What distribution? This is the
Non-distribution.
Non-distribution.
Non-distribution. This 157 centimeter is that new piece of information which is going to help us to estimate that.
Yes, that is a prior. That is called as a prior. Actually, that is a prior information which is given to you, and it will have some distribution to it. So it is also because it is also based on some information. We can assume that it also can vary, right? Because that information is depending on the samples again. But it is known to us. Like all the information is known to us. Based on that information, we can have some distribution to that. That is called as a prior distribution. And with the help of that prior distribution, we are going to estimate a parameter for a new distribution or for a distribution, and that end up actually being very close to the population distribution. Okay.
Sir, just I have one doubt.
Yes.
Sir, ultimately our goal is to find a single estimator which could represent the entire population, right?
Single estimator.
Yeah. Estimator means from the
single parameter value.
Okay, but single estimator, so it depends on the distribution, right? If it is Bernoulli, then it is having one parameter only. Right?
No, whatever the distribution be it for a said population, we don't know its distribution. We want estimated to estimate the its parameter, right?
Correct.
So that would be a single parameter, or maybe like it could be sigma, it could be mean, and many more estimators, but that will be a single fixed parameter in each moment. So if in this method, like what you are saying in Bayesian estimation, we are categorizing a bunch of samples which
no, we are not actually going for a bunch of samples. We are going for only one sample actually. I'm just giving you the
different sample is giving us different parameter.
See, so we are going to actually deal with only one sample again.
So ultimately, but how we can say that this parameter is representing the entire population?
Because along with this sample, we have some prior information. Okay, we have some prior information, right?
So given that thing,
given this information
is coming. Okay.
Yeah. So given this information, how this
prior information means that we know something about it.
Yes.
It is around like this, or it would like.
You mean to say that?
Suppose you are giving the example.
Okay, I will tell you one. Okay, I will tell you one simple example. Just okay.
Hey, so just 1 minute, one second. These all
one more question.
Just a minute.
Okay, talk at a time, because see, I don't want this.
These all random.
One more question, please. How in Bayesian theta is treated as random variable?
Okay, I'll come to that. No, we have just started. No, see the thing.
Go ahead.
Either I will explain it to you like from the starting, or maybe you can just. That's why I asked you until what point you have studied. If you have studied all the things, it's fine. Then wherever you're having doubt, I can start from there, right?
These are conditional, I think.
Yeah, these two questions which are in your mind, right, that will be actually answered in the lectures. So we'll actually go through that, like, okay, how this information will affect the final estimation or everything. Look, I will come to that slowly. Okay, but I just wanted to set up the thing. Okay, how this method of moments and maximum likelihood is different from the Bayesian estimation, right? So method of moments and maximum likelihood was basically based on what? The sample chosen, right? And in Bayesian estimator, what is happening? I am having some prior information to that distribution, right? And or to the so this
to estimate the parameter.
Yeah, to estimate the parameter. So this information will help me
to
estimate the parameter better. Yeah, I'll tell you how this will affect. Okay, so let's
actually I don't know what is the meaning of prior. Prior information means something from somewhere previously. That it would lie, the mu will lie around this, the sigma will lie around this.
Yes. So for example, let's say let's suppose if I wanted to know that what is the literacy rate of India. Okay, if I wanted to know the literacy rate of India, in year, let's say 2022. Okay. Okay, but we have census. I think the last census happened when, I think 2011, right? So if I take the data from the 2011 census, and I will get some information from that census that, okay, this was the literacy rate of India at 2011, right? With that piece of information, can I able to, you know, find
predict the
literacy,
population, or
right?
Some
Literacy rate
sort of information in the current census.
So how, and I'm not going to do all the census. What I'm going to do, I'm going to pick only some sample from this population. Okay, I will take the information from the previous data, and with the sample, with the help of this sample and with that information, I'm going to estimate a parameter, or I'm going to estimate the literacy rate of India, right? So in this case, what is helping me? Suppose the literacy rate of like Indian population, I don't know what is the exact number, but let's say it was 50% or something, right? Suppose it was 50%. Now, if I say that, can it affect the literacy rate for this population, current population? It will affect, right? If I know prior that it was 50% previously,
yes, sir.
It is definitely be around that 50% value, right? It cannot drastically go like to 20%, or it cannot go drastically to 80 or 90%. Right? It will be around that.
Yes, sir.
So with that information, if that information was not there, and only I have picked some sample, I can end up with getting the value of that parameter or that literacy rate to maybe 20%. Can I directly say that, okay, this 20% might be the Indian literacy rate, right? Or literacy rate for the Indian population. But if I know prior that, okay, this is the 50% for 2011, that means it will be around that 50%, right? It will not drastically be 80%, or it cannot be to 20%, right? It will be like, it can be 48%, 47%, or it can increase to, let's say, 54 or 55%, right? It cannot go more than that, right?
Right, sir.
So with that information, I'm able to better estimate the parameter, right? So that is the meaning of prior distribution, or prior information.
Hello, sir. I joined late, so sorry for interrupt. Sir, earlier in week 9, we are estimating estimator, right? For likelihood method and maximum likelihood method and moment method, we are finding estimator, right? So, but how do you find parameter? Here we did not find parameter, right? We are finding estimator.
Estimator is actually estimator is for what? It's for parameter only, right?
Parameter, yes.
Yeah, so it's not different from what we are finding previously. Previously also we used to find a estimator for a parameter by different methods. Those were method of moments and maximum likelihood.
Yes.
The only thing was we considered that parameter to be constant. We are not saying that it is having some distribution. We said that parameter was constant. Now tell me with these two methods, what is the estimator for that parameter? Now in this case, what we are saying that this parameter itself is a random variable and it is having some distribution. It is changing. Okay. And what is the distribution for that? That means what we are doing here is, initially we were saying that parameter is a constant. Now we are saying that the parameter is having some tolerance. Okay. So, okay. For example, let's say I'll tell you. So previously I was saying that theta is constant, right? So let's say x1. 1 minute. Just let me finish. Then you can actually talk, right? So let's say it is Bernoulli P, and this P is constant. That means I can say that, okay, it is whatever value I'll get with this method of moments or maximum likelihood, I'm saying that, okay, it will be 0.5 or 0.45, it is constant. But now with Bayesian estimator, what I'm saying is it is having some distribution. That means it is having some tolerance limit, right? So tolerance means what? Or maybe it is having some interval. For example, this theta can take values from 0.45 to 0.55, right? So I'm saying that this population is distributed with Bernoulli, or maybe and it is having, or the parameter, right? The parameter means here the probability of success for that Bernoulli trial, it can have values between 0.45 to 0.55. Okay. So now what I'm saying, I'm giving a range of values that choose these values for that parameter. It will be very close to the population parameter. For understanding. So that is the difference. So previously I used to say that, okay, this is constant, it will have one fixed value. Now I'm saying that it is not constant, it is having a range of values. But what I'm sure is I can say that value of that parameter cannot go more than 0.55 and it cannot go less than 0.45, right? So it is in between 0.45 to 0.55 based on my previous experiences.
So earlier parameter is a constant, right? We are estimating the estimator. Let's we have got some value for estimator. So what is the value of a parameter? We don't know value of parameter, right?
Estimator is a parameter only, right? I'm not understanding. It's like, see,
okay, no, I am confused.
Estimator is what? Estimator is a
you're just subtracting, right? Okay.
See, if I'm saying IID Bernoulli P, so I'm just finding a parameter. So P is what? P is a parameter. I'm finding an estimator. Estimator means what? I'm just finding the value of P only, right? I'm finding value of estimator only, but see that value I'm not sure of, right? Only I'm saying that okay, with these formulas or with this help of these methods, I'm saying that this should be the value.
Yes.
Right? So the estimator is nothing but the value for the parameter, but it is not the actual parameter value. It's a estimate for that parameter, right? This is the what I'm saying, that with the help of this method, I'm able to calculate this value, and this might be the value for the distribution or value for the parameter for that distribution. Okay,
sir, go ahead, sir.
Right?
Yes.
Okay.
So sir, we can say known distribution is a prior.
Known distribution is
known
prior.
Distribution
Yes,
is
it is a prior. So for example, let's see this example here. It is Bernoulli P, right? IID Bernoulli P, and I'm saying that suppose that this P changes from uniform. So P will take these two values. Either it will have 0.25 and 0.75. How can I'm able to say that this P will take this value based on prior information, right? Prior information means based on the information or the knowledge available to us from the previous occurrences or previous whatever the records are there. So according to that records, I'm saying that this value of P is distributed uniformly with 0.25 and 0.75. What does that mean? So this is discrete one, right? So this P will either have value 0.25 or 0.75. Now what I'm going to do, I will collect some samples, okay, and with the with the help of this sample and with this information, I will try to find the value of P, right? I'm trying to find the value of P, and to do that, okay, so let's okay, so here if you see, P is distributed uniformly with 0.25 to 0.75, and see, now that assume P is chosen first at random, right? According to the above distribution. Once P is chosen, the sample are drawn according to Bernoulli P. What does this mean now? So given that the value of P is like this.
So what is the prior? So he is 0.25 to 0.75. It lies between this.
This is what? This is 0.25, 0.75 is what? No, but this uniform
parameter itself having a distribution.
It is uniform distribution, uniform discrete distribution, right? It is not between 0.25 to 0.75. It can take either 0.25 or 0.75, right?
It is the distribution of distribution.
Yeah.
The distribution of the parameter itself.
Yes.
We have curly braces. Yeah.
So it is having probability 0.5 and 0.5, right? Correct?
Yes, sir.
This is discrete distribution.
So sir, in Bayesian, we will always have this interval of parameters, right?
Interval of parameter,
or
the distribution for a parameter.
Yeah.
This is better to say, right?
Yes,
or okay. So this now I know that my P is distributed uniformly with this 0.25 and 0.75. So what is the probability for P taking value 0.25 is 0.5, right? And what is the probability that P will take the value as 0.75 is 0.5. So this is the discrete distribution, right, for P. Now, given that P will take this value, so let's say P will take P equals to 0.25, right? So given that P is having this 0.25 value, and with this sample S, what is the probability that, okay, I will just go there directly, maybe, okay. So, okay, this is the sample taken, that's okay. Okay, if you are not speaking, then somebody is having some noise, right? It's very, okay, maybe I'll just, okay, this is somewhat clear here. Okay, so what we are finding here, what is this? This is probability that
conditional probability.
P will take value 0.25 based on this sample.
Correct. So right. So and to find that probability, what we have done? What is this? So okay.
So we are using Bayes rule, sir.
Yeah, Bayes rule, but what this interpret? So given that P equals to 0.25,
just joint probability, sir.
Right. So given that P equals to 0.25, what is the probability that this sample is taken from this with this probability, right? Correct?
Yes, sir.
So if I use this, and what is this? This will actually called as likelihood.
Yeah, sir, this is likelihood.
Right? This is likelihood.
Yes, sir.
The first term is likelihood.
First
I'm confused, sir.
No,
First term is likelihood.
Yeah, this is likelihood. This is likelihood, and this is prior. Right? Okay. So
yes, sir.
So see that given that
first
P
we calculate the likelihood of P equal to 0.25 now.
Correct. So okay, why you guys are confused? Okay, I'll tell you this probability that this term, okay, probability that the sample is taken. So sample.
How okay, go ahead.
I'll just tell you like 1
Sir,
when that P equals to 0.25, right? This probability I'm calculating, and why I'm saying this is a likelihood. So previously, how you guys used to find a likelihood?
Multiplication of the probability.
No,
this
that
is
is
just
okay.
used to assume the parameter. Assume the parameter
correct.
P.
So
and then we used to find the probability of that.
Right. Correct.
As event.
So then that means it is what? Likelihood, right?
Yeah. P.
Likelihood of P equal to 0.25.
So because here I'm saying that P equals to 0.25, which is constant, right?
Yes.
So given that if this is constant, what is this? This is sample, right?
Yeah.
So previously we know that this was constant, P was constant, and now I wanted to find a likelihood. So I used to take the samples and I just used to do the multiplication of the probability, right? Based on the distribution, right? So same thing I'm doing here, and hence I'm saying that this is likelihood. Okay, and this P equal, what is this probability? Probability that P equals to 0.25. What is this? What is the value of this?
0.5.
And 0.5, right?
Information provided to us.
Because it is uniform.
Yes. From where it is coming? From here it is coming.
From the non-distribution.
So that means this is my prior distribution, right? So I'm saying that this is prior. Okay, and this is likelihood, and this is called as support. But actually, support will be a constant. Okay, so we are saying that this probability, okay, this probability actually gives me the estimate for that parameter. Okay, what this probability will give me, given that this sample, right? Given that this sample, what is the probability that it will belong to this parameter will take the value as 0.25, right?
Yes.
So it is the probability of success when we are considering a parameter to be of a certain given value.
Right. So that means based on what? Okay, tell me where.
Can you explain it in terms of conditional probability only? Probability of A conditioned on B. It is like that only, no, sir?
That is very easy, no? Probability that A given B is what? I'm just giving you the intuition behind this. I don't have. Okay. So okay.
That is what written here.
That is okay, but what I suppose is like a lot of people don't understand the like why this is likelihood and prior. Okay, but what will be this like? There is nothing in it, right? Probability that A given B is what? Probability of B.
B condition on A into probability of A. Upon probability of B.
No, sorry.
Guys, let him speak.
Sir, probability of B,
right? B. But what is that like? I don't understand. Why this? How does this help you to understand this?
How they get probability 0.25 whole to the power 3? So that part I didn't understand. How did they
because
get?
Ajay,
this is likelihood,
right? For probability P equal to 0.25.
I'm saying that given that P equals to 0.25, and what is the probability that it belongs to the sample S. So if I say, what is this probability of success, right?
Yes.
So given this sample, how many times? Okay, one belongs to what? Probability of
3 times.
No, probability of success, right? One,
success.
And 0 is?
One belongs to success, 0 failure.
Failure. So if I say that this P equals to 0.25, that probability of success is 0.25, and then what will be the probability of this sample? It will be 0.25, right? Yes. Into 0.75 into 0.25 0.25 into 0.75. So it will give me 0.25 to the power 3.
0.25, okay.
And this is likelihood actually, right?
Yes. Got it, sir.
Okay, so this P of S, don't worry about this because this is actually is going to be constant. It does not, help in finding the estimator. So for now, what you have to think is.
So during lecture, professor told it as normalization.
Yeah, normalization only. Okay. That does not just. So you can study more if you wanted to do that. But the crux of it is what? If I wanted to find a parameter, this parameter, the probability of that parameter is directly proportional to what? Likelihood into prior, right? You're understanding the point?
Yes.
Okay. So why I'm using directly proportional? Because this becomes constant. So this does not actually. So as he said, that actually it gives me a normalization, right? So it doesn't matter.
Sir, this I do not understand. Divided by P of S, what happened to P of S?
This is what is P of S? It is probability that that probability of sample choosing, right?
Choosing that sample, yeah.
So it actually does not help in so if you go through this if you see, if you are choosing the parameter the sample, right, it does not actually help in finding the parameter because whatever sample you have chosen, it does not affect the value of P, right?
For 0.25 and 0.75, PS is same. So you can
same,
say
right?
Sir,
because
in my opinion, sir, PS is like we are adding all the probabilities of in the distribution, prior distribution. For example, probability of 0.25 plus probability of 0.75 is equal to PS. Had it been 3 terms, it would have been, say, suppose it had been 0.25.
What does that mean is,
for some,
what does that mean is it is constant, right? For the given.
Yeah, it is constant, and we are calculating probability on this constant.
Correct. So it does not
like for total number of cases of probability. What is the probability of getting 0.25 over all probability of getting 0.25?
Still, I do not understand.
0.75.
Sir, third 0.25 to the power cube. How does it come?
I told you no.
I don't understand.
I don't understand.
Smiley, I can explain.
Here is
what is P of S.
It's not smile. I'm not speaking. It's not my doubt.
No, 1 minute. It's just okay. So just think clear about this. So the first thing is this about this, right? 0.25 cube into 0.75 cube.
Yes.
How does this happen? All right, right?
Yes.
So what is this? This is this value, right? Probability that given that S, right? So given that P equals to 0.25, what is the probability that this sample
is yes.
So what is the sample? Sample is this, right?
Yes.
Okay. So x1 equals to 1, x2 equals to 0. What is the probability that x1 equals to 1? Given that P probability of success is 0.25. What will happen?
This
is 0.25. What about this?
0.75.
0.75. What about this?
0.25.
And 0.75.
750.
And if I multiply these probabilities, it will become what? 0.25 cube into 0.75 square. So actually, this is what you used to do with likelihood, right? When you are finding for maximum likelihood method, when you find the likelihood, what you do? You just
We are multiplying each
right. So you
probability density or probability mass function. We are multiplying each.
Correct. So same thing we are doing here, and from
Sir,
there
if it
only.
is not a independent, so we can't multiply, right?
Right. It will always be dependent. The sample taken is always be independent of the other, right?
Okay.
And about this, the probability of S, right? So the sample chosen does not actually depend on the value of P, right? So whether the value of P is 0.25, I'll get this sample only, right? Or whether the value of 0.75 is there, the sample won't change. The sample will be same, right?
Sir, but if P of S is same, then what is the point of P of S given that P is equal to 0.25? So it is changing accordingly, right? If P would have been 0.75, then P of S given that P is equal to 0.75 will be different.
Okay. What you're saying again? Can you please say?
So I do not understand how you're dealing with. The only thing, like you said, is it is not depending on whether P takes the value 0.25 or 0.75, right? And I'm saying this, the same thing that you explained right now, likelihood, the same thing. P of S given that P is equal to 0.25. If P would have been 0.75, then P of S given that P is equal to 0.75 would be different, right? So it is depending on whether P takes the value 0.25 or 0.7.
No, what is P of S? What is P of S here?
So P of S is total probability.
Probability of choosing that sample.
So what will be okay, choosing that sample, right? So yeah, so somebody said, right, it's total probability, right? So how will you calculate the total probability?
Like
the sum of these two.
Sum of what?
0.25 cube.
It is nothing. Total probability is probability of
plus
P equal to 0.25 plus P equal to 0.75.
So you know the base rule, right? In the base rule, so what is the numerator is there? So probability that S given that P equals to 0.25 into probability that P equals to 0.25, right? Plus probability that S given P equals to 0.75 into probability that P equals to 0.75, right?
75.
So,
yes.
So even if however you choose that sample, right? That probability of that choosing the sample will be same, right? See, we have already added this, right? The denominator will always be the addition of this,
constant,
right?
it's constant.
It will always be a constant, right? You're understanding? See, this is a total probability, right? You can think of in that way, the total probability. So if you see the base theorem, what will happen there?
I understand that we can add those two values and I will get the P of S. I understand that.
Right. So I think so it will be like this, right? Suppose if I have only two things, right? And okay, then what we used to do there, base theorem, we'll add these values, right?
Yeah.
For total probability, correct? So in that case, whether this value will change, right? If this value is something else, right? So, or the sample chosen, will that affect the value of parameter P? Sample chosen.
No, sir. Why will that? We have non-distribution of P. Why would that impact this?
Okay. Correct, right?
But sir, the
maybe
probability of sir, I understand we can add that. I totally got that thing, but I have doubt this independent thing that you are saying. This does not depend on that. I'm not getting what does not depend on
one
what.
minute. Oh, okay, 1 minute. Ishan?
And so what is this in at the right hand side 0.25? How it came?
Where?
So right hand side of that
It-
equation 0.25.
Okay, so
Uh,
you can calculate. No, what is the value? I don't see.
so we are not getting that
Why?
0.5.
Why not? So what is P of S? How to calculate P of S here?
It is given here, na, sir, P of S.
Where is the value? P of S.
We can add these two
Yeah,
things.
here,
I
it
think
is there.
P of S is calculated later
Yes.
on, and then that value is put over there to get this value.
So it will be 0.25 cube. Cube notes. Okay, cube.
Will be 0.25 only, sir.
0.75 square into 0.5 divided by this value. So this will get cancelled. Yeah, we'll get with 0.25, right?
Yes, sir. Yes. Sir.
So how you calculated this P of S?
I understood that, so we just added both of those values. It's just what do you used to call it? I do not remember the name.
Total probability.
Yeah, law of total probability it is.
Yes, law of total.
So we just added that.
So the thing is, okay,
constant.
it is constant, right? It is, so in this case, it is constant. So suppose if this is my formula, right, to estimate a parameter, right? If I'm going to find a distribution from here,
so this constant thing I'm not understanding. What
why
is
not?
constant?
Why I don't know? See this P of S. If you add, okay, just tell me what if any value if I change here, it will give me the constant thing, right? I don't understand like why the total probability will always be constant, right?
Okay, so the probability that P will either take this value.
So why you are not saying that this value will not be a constant?
Sir, I mean, can you just elaborate this constant thing? Constant with respect to what? What do I change with respect to which it is not changing? With
samples, I guess.
Look at these two equations. The first the first star and the second star. Look at the first star and the second star. PS is constant in both the cases. So probability that P equal to 0.5 given S is proportional to the right hand side, and PS is constant in this case. Similarly, for the second star also, P equal to 0.75 given S is
P of S is same for both. Yeah, that I understand.
Yes. So that is why PS is constant. So we can say that this conditional probability that P equal to 0.5 given S is proportional to the remaining portion.
Only this numerator, right? And why we are doing these two things? To estimate a parameter, right? And actually it will give me the probability value only, right? Okay, so if this is the parameter, what is the probability given that sample?
This actually it is referred in the lecture as posterior probability, or
posterior distribution. So anyway, this is a distribution. So again, it is it will give the value in terms of distribution only, and so anyway, you will get to know that okay, if it is the distribution, then maybe you can use the posterior mean or maybe posterior mode or any other value to to find the estimate. Okay, I think I don't know, like, okay, again what to explain here. So I just
all those three stars are clear. Then can we move on to calculating estimator now? Like,
yeah, that's what I'm. So here, so if you see from here, the first thing, right, is 0.25. The value is 0.25, and the second thing is 0.75. So which is which is the greater value?
0.75.
0.75. So here I'm using posterior mode, right? So that means, right, because I'm saying that. So what it gives me? It gives me one distribution for P star, right? So P hat, right? So P hat value will be having 0.25 and 0.75. These two values it will have, and the respective probabilities will be again 0.25 and 0.75. If I wanted to use posterior mode, the value will be 0.75, right? Because it is having more probability. That means it is occurring more often. That means if
more
I use,
likely to be 0.75
right,
than 0.2.
So this might be one estimator. You can use another estimator. Like for example, if I wanted to use posterior mean, in that case, what will be the value? It will be
You have to use the
expected value or weighted mean.
Weighted mean, right? So you can
Yeah.
use that also. So here maybe I don't know. Okay. Yeah, sir has used this also, I think, right? Posterior mean also he has used. So in that case, it will be 0.625. So again, the choice is with you, right? How to which estimator we wanted to take. The estimator one gives by using the posterior mode. Second estimator gives you the value with respect to posterior mean. So to find posterior mode and posterior mean, you need to find the distribution for that parameter. And how you found out that? Using the Bayes rule, right?
So which is which is better, posterior mean or
Depends.
mode?
No, it depends. It depends. So that's why it's when you have the prior distribution, right? So it depends on that. So if you, we cannot say, right, which is the better thing. So if you have so if you remember from statistics 1, when you use mode and when you use mean and when you use median, right? So it depends on the values in the, so how many outliers are there, or how many if no outliers are there, then we can go for posterior, we can go for mean, right? So there it will be a better estimator. If it is we have a lot of outliers, in that case, if you
mean is
go
heavily
for
affected
mean,
by outliers,
right,
so we cannot go
affected.
for that. Yeah.
So yeah, it depends on the information which is there with you. It depends on prior information that which estimator you can go, right? Okay.
Yes. Yes.
Okay. So here, if this is the example, okay, can you tell me the values here now? If you guys are there, you just try to solve this problem. Give me estimator 1 by using posterior mode and estimator 2 by using posterior mean. Okay, again I need to give you sample, right? Okay, this is a sample. Just take 5 minutes to solve this and tell me the answer. Are you guys able to solve it?
Yes, sir. We are solving.
Okay, let's try to solve.
Hello, sir.
Yeah.
Could you show the previous slide before this?
Okay. You can try it, no? No?
I've already tried till where we're supposed to calculate the probabilities. I didn't understand this estimator 1 and estimator 2.
Okay.
Till here, I've already calculated, that is P equal to 0.25 given S and 0.75
Okay.
given S.
Okay. Just see and tell me now. Like here, you are able to estimator 1 is what? If you find the probability that P of 0.75 given S, right? If so, in that case, it
Yes.
was 0.25, right? So okay.
Yeah.
Okay, this value is 0.75, right? Here,
Yeah.
right? This value is 0.25,
And
right?
this is 0.25.
So that means 0.75 is greater than 0.25. So if I use this estimator 1, I will go with the higher probability that the sample is taken where the parameter value is 0.75, right? So given the
This is
sample,
which
what is the
method of estimation of estimator? Base.
base estimator 1, right? So see what it is saying, because it is saying that given that sample, right? Given this sample, what is the probability that this parameter of
P
this
will be
distribution
0.75 is greater. Its probability is greater. Yeah.
So
given the sample, 0.75 is more likely. Yeah.
More likely to occur, right? So that what it is saying that given this sample, this probability is more likely for this parameter 0.75. So I'm saying that this distribution belongs to this parameter, right? The other thing is if I use posterior mean, how to find the posterior mean is I just taken the weighted mean of this, right? So it is given to be 0.625. So I'm saying that if I use this estimator, which is posterior mean, the value of P should be 0.625, right?
This 0.25 is the probability that P is 0.25 given us, right? This is the first 0.25 we are multiplying by. It is its own probability or what?
This is probability
Where is
that.
this 0.25? Oh, okay. 0.25 is the value we have taken of P. Okay, so 0.25 into its probability plus 0.75 into its probability.
This is how you calculate, right? Posterior
So
mean.
we're just finding its average.
Yeah, because see, if you see this distribution, this is distribution, right? So this distribution of P hat is, if the P hat value, actually what is happening here, the 0.25 and 0.75 values are there, and these probabilities are similar. That's why
exactly.
getting
The problem is
confused.
we're getting exactly the same.
Okay, but it should be like this. Provided that P hat equals to small p hat is again 0.25 and 0.75. So if this was a distribution, then in that case, how I used to find the probability? This value, okay, this is the random variable, right? This value into this probability plus this value into this probability.
Okay.
So suppose
that's how we get the posterior mean.
Suppose this was
So
it was like this 0.6.
What's the first method called? The estimator 1 we have calculated is which method?
This is called posterior mode. This is nothing but mode, right? It is a mode, right? If this probability is higher,
mode, and that is posterior mean. Yes.
Because this probability is higher. If this probability is higher, that means the value, this value is coming more likely, right? So it is occurring more. Right?
That is 0.75. Yes. And
so
if
here,
we were to posterior mean, then we get that. Okay.
So here I think you will be able to
solve it, sir.
Yeah, okay. So I'll again solve it and just see that if it is correct or not. So if I wanted to find this probability, how to find this? I'll use what? Likelihood, right? So maybe the likelihood will be it should be p to the power. So for 0.25, okay, I will just write it again. Probability that p equals to 0.25, given that s is given p equals to 0.25 into what is it? 0.25 given p of s, right? So this value will be 0.25 cube into 0.75 square, right? In
It is
into
divided by pointer PS. Divided by PS.
0.9.
this I wrote it like divided by only. Okay. So okay. What is P of S? Can you tell me?
So it is 0.25 square into 0.75 square into 0.3.
Final value. Give
Yeah,
the
final value. Say
0.25.
Square.
Okay, 0.25.
Square. 0.75 square into 0.3.
Okay. All of you understand, right? How to find this P of S? It should be this value plus this value. 0.75 given S will be equal to P of S given P equals to 0.75 into P of 0.75 divided by P of S. So this will be 0.75 cube into 0.25 square into 0.1, right? And divided by P of S. So actually P of S is what? This value plus this value, right? So this is the final value. It is coming to be 0.25 square into 0.75 square. So what is the value here?
1.03.
So in the first 0.75.
Is actually
0.75, sir.
Okay. It's 0.75. Okay, correct. Here it will be
0.25, sir.
Okay, because this is 0.75, then it will always definitely it will be 0.25.
0.25.
Right? Okay.
Well, it is weird, sir. Value 0.25, it is 0.75.
Okay. Yeah.
Like the value P could have been taken difference, right?
Yes. Right.
Exactly.
So it because we are why it is happening, because you see the distribution, right? Prior distribution. 0.25 is having probability 0.9, right? So this will affect this probability, correct? With the prior information will affect the value. So that is happening, right? So that is why we are getting this higher probability for 0.25. Correct? Right, no?
Yes, sir.
Yes.
So the distribution of P hat will be so it will take two values, 0.25 and 0.75. And now this probability that P equals to, sorry, P hat equals to small p hat
0.75.
0.75 and 0.25. So now what will be my estimator one?
Mode will be
Sir, it will be 0.25.
It will be 0.25, right? That means the value of P will be 0.25. And what will be my estimator two?
0.375.
It will be 0.3. So how it will come? 0.25 into 0.75 plus 0.75 into 0.25.
Yes.
So it will be two times.
We really changed it. This is such a confusing one because we're getting the same values 0.25, 0.75, 0.75, 0.25. So it's not clear how the formula is being applied.
But anyway, the thing is,
it's very prone to confusion.
Yeah, but you understand the flow of the equation, right? Like how it is going and how, and you can think about from this prior distribution itself that if it is having higher probability for this value, that is actually coming here, right? So you can say that probability is higher for this. If the sample is different, then you can have different probability, but it is higher chance that since it is having higher probability, it is the probability for this occurrence of this parameter is higher, right? So the value of this parameter will get the higher probability based on what? Based on the prior information. Okay. So let's see. And if you consider one more thing is, if you remove this also, right? If you remove this also, can you calculate this probability here? This value, the multiplication of this, only the numerator.
Which value, sir?
This one. Yeah, this one. Numerator 0.25 cube into 0.75 square into 0.9.
Okay.
Whoever numerator will be higher, that will be the mode.
Yeah, but can you tell me the values?
Sir, it is 0.0079101563.
Okay, done. Okay. And what about this?
That's 0.75.
No, only the numerator.
Only the numerator.
So first one, sir, it is 0.002636717875.
26, sir.
Yeah,
Somebody
26. No, sir.
Okay.
26. 36.
Okay, that's it. Okay, that is okay. 26 is okay. Next. Here.
And for second, it is 0.0079.
You are talking about 0.25 or 0.75?
So
79.
actually, you told vice versa. It's
It should be 7.
for the top one, and the 4.26 is for the last one.
Right?
So I'm talking about P is equal to 0.25.
See, it should be higher, right? Because this anyway, this will be right. This is the denominator here and here. It is same, constant, right? It is not actually affecting the value. It will actually give me the normalized value, right? So if I don't consider this also the denominator, why I'm saying this? Because if I'm saying that if you don't consider the denominator also, I'm able to say that okay, this will have the higher probability, right? So I can directly choose from here itself by looking at the numerator, right? You're understanding the point?
But sir, we cannot get as a mean estimator, posterior mean estimator.
We'll get. So I will tell you how we'll get. So because this was Bernoulli distribution, we don't have the formulas for that. But if it belongs to beta distribution or gamma distribution, right? In that case, you know the formulas, right? Alpha upon alpha plus beta for posterior mean. We will come to that. Okay, we'll come to that. But okay, the one thing you can see that here it is higher and here it is lower compared to this, right? And if I use this denominator also, I will get the same thing. So same thing means not the same value, but the
same comparison, comparatively same.
Yeah. So the comparison which we are going to make based on the values, it is same. The comparison is same. Okay, let's move on to the. Maybe I can just skip here. Okay, so that is what we have already seen, right? So this parameter was having some PMF or PDF, that is we have already seen here now. Okay, so posterior probability that is proportional to likelihood and prior. This is what already we have seen, correct?
Yes, sir.
Okay, so I think okay. So here sir has mentioned that it is normalization and it does not depend on the value of theta, right? Okay, so that you can actually study okay. This thing. Choice of prior, is it clear to all of you? What is flat and informative and conjugate and informative priors? So flat and informative means it is if it is uniform, right? It does not add any value to the parameter. Okay, somebody is speaking there.
So flat means uniform.
From where it is coming, that noise?
No, it is stop. Smile.
Okay. So flat is what?
Uniform, sir.
Flat is what?
Means
correct. Flat is uniform. Okay. Flat prior means it's a uniform prior. And what is the PDF of or PMF of that? No, sorry, not PMF. It should be PDF. So what is the PDF of uniform prior?
1 upon B minus A.
So that means it is a constant, right? It does not add any value to or it is not giving you any information. But if you go through the formulas, you can understand that it does not because it will take the values in that interval, but it does not give any or it does not affect the posterior distribution, and hence it is called as uninformative prior, right? So here you can see that it is nearly flat over the interval in which the parameter x value. Second point is this usually reduces to something close to maximum likelihood. Okay. What about conjugate priors? It is we are going to pick a prior so that the posterior is in the same class as prior. For example, if I have prior as normal, what does it mean by prior as normal?
Normal 0.
Normally distributed.
Yeah, and if so, what does that mean? So let's say Okay, I just wanted to say, okay, my values. Okay, so here suppose it is x1, x2 to xn, right? It belongs to some IID x, okay, and or IID x with some parameter theta. Maybe I'll say that IID Bernoulli. Okay, it should not be Bernoulli. Okay, let's say Bernoulli P. Okay. Then what is the distribution of prior? What does that mean?
Distribution of P.
Right. P is having distribution normal from, let's say, mu1 comma sigma 1 square, and in that case my posterior density will also have a normal
distribution.
So but yeah, definitely the parameters of that, so that mu1 and sigma 1 will not be mu1 and sigma 1, it will be something else. We'll see that also. Similarly, if my prior is beta, then my posterior is also beta. In that case, when my prior distribution and the posterior distribution is same, it is called as a conjugate prior. So there are certain 5 or 6 priors which are like always give you the conjugate, so always give you the same posterior distribution as that of prior. They are called as conjugate priors. You will get that information from anywhere, like from internet also. If you search, you'll get the conjugate pairs. You can just check for it, or maybe in the lectures, I don't know, like if it is mentioned there or somewhere, I'm not sure about it. But yeah, so if the prior is normal, your posterior will also always be a normal. If my prior is beta, your posterior will always be a beta. So these pairs are called as the conjugate priors. Okay, informative priors means based on some information, based on the past information, we are having the distribution of prior. In that case, we'll.
So what is this parameterize the prior so that its flatness can be controlled? I do not understand.
That means flatness means what?
Uniformity.
It is uniform prior, right?
Uniformity.
Uniformity. So that means you are not saying that the probability for each value taken by that or which value in that interval will not be same. It will have different probabilities, right? So it is not always be having the uniform distribution. It will have some other distribution. Suppose it is having some other distribution, means it is having, suppose let's say, exponential distribution. In that case, will that be a flat or will that be a flat prior, or will that be it will not be a
flat prior, yeah,
right? Because for each value taken by that random variable, it will have different probabilities, right? That is called as the
informative.
Informative prior. Or
but I do not understand this line. I understand that it is not flat, but parameterize the prior so that its flatness can be controlled. What does this mean? Flatness can be controlled, uniformity can be controlled.
So what do you mean by that? That flatness can be controlled? That means you don't want the flatness, right? Because I wanted some information, right? If I have uniform prior, then I will not get any information from that, or I am not going to use that information, or it will not affect. It cannot affect the parameter, right? It will not affect the posterior.
Why any given informative priors may approach flatness if they are of a certain distribution, unknown distribution? They should follow the distribution continually. Why they would approach a uniform? They would become a uniform.
If you whatever information you have collected, suppose it is not collected properly, or it will, let's say, it is giving you the same probability. So for example, what do you mean by the information collected is, let's say, if you wanted to find, for example, if you wanted to find the height of a person, right? So in case whatever records you have taken, right, until now, or whenever you stop the records, suppose let's say you have got 10 values of heights, okay, and every value, that means, suppose, how you will get the probability? You say that, okay, this 150 centimeter height will have 100 people, okay, again 151 centimeter will have again 100 people. So for each of that values taken by that random variable, or maybe that height, So we have the same probability, right? Because almost for every value, we are having the same number of people, right? That means same probability. That okay, probability of getting that value is again same. So in that case, it will be a flat prior, right? But
Yes,
in
sir.
general life, okay, in any real life scenario, we don't have such kind of thing, right? We'll always be having range of the values taken by a random variable, and it will not have the same probability. It will have different probabilities, right?
Yes, sir.
So mostly, if you take the information from real life, right, you will get some certain distribution, which might not be exactly fit to some known distribution, but it can be very close to some other distribution, but it will not always be very close to the uniform distribution, right?
Yes,
You
sir.
can take any example. I don't think it will be very close to the uniform distribution. It will have some other distribution, but it will not be close to uniform distribution. Correct?
So, sir, by parameterizing them, are we assigning them to different intervals or certain kinds
No.
of parameters? What kind of parameters are they?
Like, so that parameter itself, that prior information, that non-distribution we have, it have its own parameters. That's what we are talking about, right?
So this P, right?
Like,
Okay.
yeah, P is distributed
this
normal.
P is this. Yeah. So it is having these parameters, right?
Yes,
It's
sir.
mu1 and sigma 1 square, right? So these are the parameters, right? But these are not very these are not indicating the flatness, right? Because if it is normally distributed with mu1 and sigma 1 square, so these two are other different parameters, correct?
Yes,
This
sir.
is one parameter. These two are again two different parameters. So we have parameterized this P such that it will have some other parameters, but that does not belong to what? Flat prior. Or
yes, but what does this mean? Flatness can be controlled. If there is no flatness, what are you controlling? I do not understand it.
Okay, leave that. Okay, so maybe you can actually just go through the lecture. Maybe sir has I'm not sure. Like, okay, I just wanted to say that this should not be like this. Okay, what I understand is, okay, it should have some two parameters.
So basically, we are defining the parameters, which are actually P, the random parameters, by the prior information through which we got.
And it will have some other parameters. Okay.
Yes, sir.
Okay.
Like parameters for parameters.
See this line also. If you are getting confused to it, leave it. It's not like it's not any of much information or knowledge giving to you, right? It's fine. You just understand this scenario that okay, if this is the sample taken from this distribution, which is distribution of a population, it is having some parameter and it is unknown parameter to us, and to estimate this parameter, I have some information, prior information, which again will belongs to some other distribution. So in this case, it is normal and it is having two other different parameters, right? But these are known to you. This mu1 and sigma 1 is known to you. So with this kind of information, can I able to estimate a parameter for my population? This is the scenario. Okay.
Okay, sir.
No need to go like line by line or word by word, but this is the broad thing to understand, right?
Okay, sir.
Okay. So suppose the uniform. So okay, you can actually go through this uniform prior. It does not actually help you in or it does not. So let's say this question is there. So this p to the power w into 1 minus p to the power. What is this? This is likelihood, right? Yeah, but this is likelihood, right?
Yes.
And this prior density actually is constant 1, right?
1.
So does not if this prior density was not there, right? Does that affect my posterior density?
No.
It is not going to affect, right?
It's a constant.
It's a constant. So that means that is why we are saying that this information of prior is not adding any value or it is not affecting my posterior density, right? And hence it is called as flat prior. Or
sir, can you please explain it again, sir? Why it is not adding any value?
you can see, right? So suppose if I don't know this prior density, right, what will be my likelihood? If I don't know the prior density, I just, okay, suppose I have the samples 1 0 1 1 0. Okay, what will be my likelihood in this case?
P raised to 3
P raised
1
to
minus
power
P raised 1 minus P raised to square.
And suppose this is my posterior density, right? In this case, I haven't considered the prior density, or I did not consider any previous
Prior
information.
density is 1, so it does not matter. Prior
So,
density
right, so here p to the power 3 into 1 minus p to the p square, and again it is again belongs to what? Beta distribution, right?
Yes.
And if I use this information, right, prior density, so what is the prior density here?
1.
Like 1 means what? It's a constant, right? So if it was 2 also, suppose this p was belongs to uniform 0 2, what
Then
will be?
also it is constant.
It is 1 by 2, right? So it will be 1 by 2, right? So in this case also, my posterior density will be what? Same, right?
Posterior density will be proportional to the likelihood.
Only the likelihood. Only the likelihood. It is not
Only the-
affect. It is not taking
because
any
then prior is constant.
constant, right? If this value belongs to 0 to 4 instead of 1, what will happen? Its prior density will become 1 by 4. Again, does it affect anything here in the distribution? No, right? Because whenever we are saying that it's directly proportional to something, then in that case we are not considering any constant, right? That is why we are not considering that p of s, right? The denominator. We are saying that it, because it is constant, we are not going to consider it in the in the posterior density, and hence we are saying that posterior density, it is not equal to likelihood into prior density. It is directly proportional to likelihood into prior density, right? So when my prior is uniform, then that means it is not adding any or it is not affecting my posterior density. Density is called flat or flat. Okay, anyway it is flat because it is taking it is flat only. You can see from the distribution, right? If it is 0 to 4, then that means it will be having value 1 by 4 over this range, right? 0 to 4, correct? So you can see it is flat. But if you see here, my posterior density is not changing, and hence it is not giving any information, or it is not adding any value, and hence it is called as a non-informative prior. Similarly, if we will check one case of, okay, we'll check in case of maybe, yeah, okay, beta prior. Okay, so here what is happening? This p is having distribution with respect to this, right? Beta, alpha, comma, beta, right? So what is the density of this prior density? P to the power alpha minus 1 into 1 minus p to the power beta minus 1. But this p is different, okay? This is small p, right? This p is different, correct? No? This darker p,
yes, sir, yes.
This darker p is,
It is the
parameter.
Yeah, but the lighter p is the parameter of darker p.
Right. Yeah. So it is p to the power alpha minus 1 into 1 minus p to the power beta minus 1, and this p lies between 0 to 1. Okay. So some sample is taken here, right? Suppose okay, we'll take one example here. Suppose my sample is 1 0 1 1 0. Okay. In that case, what will be my posterior density? Posterior density is directly proportional to what? Likelihood. What is likelihood here?
P to the power 3.
P to the power 3 into
1 minus p to the power
2. Okay. Right?
And p multiplied by the
into
prior. P raised to alpha minus 1.
To the power
alpha minus 1.
Okay. Do you want to take any value to alpha and beta?
Yes, sir. Take 2 and 3 maybe.
Okay. 2 or 3, or maybe some 3 4 will take, because I don't want to confuse with this alpha and okay. So here it will be p to the power. Okay. No. So it's alpha minus 1, right? Okay. 2 3 is fine. 2 3 is fine. Okay. So here it will be p to the power
1. 1.
1, right? Into 1 minus p to the power
Square.
2.
So it will be what? P to the power
4.
4
1
into
minus
1
p to the
minus
power
4.
4. Okay. So this belongs to what distribution? Beta.
beta
5,
5.
5, yeah.
5, right? But suppose this was my uniform prior, right? Suppose this was uniform in 0, 1, right? In that case, what will be my likelihood or posterior density? So it was
that will be
we will not
same
have
as
this, right?
prior density.
We will not have this. We'll have only this. So in that case, the posterior density was beta
4,
3. So okay. So initially it was
Why
like
4,3, sir? I do 4,
it should be alpha minus 1 into 1 minus p to the power beta minus 1, right? You should add 1, right? 3 plus 1 and 2 plus 1, right? So it will be 4, 3, right? Here it was 4 to 4, 4. So you added 1, right? Here, then it becomes 5, 5.
But it should be 3, 4, no, sir? 2, 3 we have alpha beta. Right.
Sorry, 3. No. This is p cube into 1 minus p to the power 2, right?
Yes.
It should be 3 plus 1, 2 plus 1, right?
2 or 3 is a prior. It's now posterior.
So it should be 4, 3, right?
This is posterior.
Yeah, that I understood. Posterior density I understood. This again that you said beta 4, 3.
No, I
Because
was
alpha
saying
minus 1 is 3 and beta minus 1 is 2. So alpha must be 4 and beta must be 3.
Okay. Sorry, sir. Yeah, got it.
correct, right? So okay, you can see that now when my prior was uniform, my beta distribution was different, right? So the posterior distribution was different. Actually, it is similar to what likelihood is. That means it is not adding any value or any information to my posterior density, right? But when I have some other distribution, it will have it is adding something because it is giving me some different distribution, right? Okay, so that is why it is called uniform is called non-informative prior. And if you have some other information given to, that means if you have some other distribution to it, will have informative prior. But now you can observe one thing. My prior distribution was what? Beta, right? And my posterior distribution is also again beta, but obviously it is having some different values, right? The alpha beta values were 2, 3 for prior distribution, and for posterior distribution it is 5, 5. Okay, so here you can say that if my prior distribution is beta and posterior distribution is again beta, it is called as what? Conjugate prior, right? Okay, so when my prior distribution and the posterior density distribution they are same, then we are calling that distribution of prior as conjugate prior, right? Okay, so okay, can you try to solve one thing here? It is somewhat difficult, maybe. Okay, let's okay, this is okay. Can you try this one? This is kind of this okay, extensive, but okay, fine. Try to solve this question. Okay, don't try to solve using method of moments and maximum likelihood. You can just check it on the lecture. Just try the second point. Find a posterior distribution and mean. Okay, just try take 5 minutes and we'll discuss it once. Okay, so is it completed?
Yes, sir.
Okay, so here the things are, I'm not going to solve it. Already, I think it is there. But so x will take values 0, 1, 2, 3. So this is the distribution of x is given to us. And probability that x equals to small x is 2 theta by 3, theta by 3, right? Then 2 into 1 minus
2
theta
into 1 minus theta by 3.
3.
And 1 minus theta by 3.
Yes, it's 1 minus theta by 3. So some samples are taken, right? So the setup is like this: x1, x2 to xn is taken from IID, which belongs to this distribution. So if it was Bernoulli, we would have the distribution like this, right? 0, 1, and provided that x equals to small x to be some probabilities, right? So I don't know, like maybe it will be, yeah, it will be p, and it is 1 minus p, right? So here, instead of this distribution, we have this distribution, right? Okay, so we have the sample as 2, 2, 0, 3, 1, 3, 2, 1, 2, 3. So can you tell me the likelihood of this?
So it is 32 by 27.
So no, okay, just tell me how to find that. So that is important. More important is what? So
these
how many
are
times is occurring? How many times we just
Theta raised to 3, 1 minus theta raised to 3.
So these are IIDs, sir. We can multiply the probabilities.
Right.
That's the basic idea.
Right. So what we have to do? So I will just find 0 is occurring one time. So that means this probability will be 2 theta by 3. Okay. Into 1 is occurring how many times? 2 times. So it will be theta by 3 square, right?
Square.
Then
Yes.
2 is occurring 1, 2, 3, 4 times. So the respective probability will multiply that many times. So it will be 2 into 1 minus theta by 3 cube, right? And then 3 is occurring how many times? 3 times. So it is 1 minus theta by 3 cube.
2 is 4 times, sir.
2 is occurring 4 times.
Okay, so it will be 2 to the power 4. And if you multiply that, then you will get the whatever, I don't know, like maybe some, yeah.
Theta constant will be there, and then theta raised to 3 and 1 minus theta raised to
Right.
7.
So how many? Okay, can you tell me what is the final thing? Theta to the power
3.
3 into
1 minus theta to the power 7.
7. This is my likelihood, right?
Proportional, yes.
So okay, anyway, it is likelihood. So I will say that then posterior density is directly proportional to what? Likelihood into prior. So likelihood is
1
minus theta to the power 7, and prior is here
uniform 0
uniform
1.
0 1. So it will be into 1, right? So anyway, it does not add up any value, and it looks like some what beta distribution, right? So it will have yeah, so it will be 4 8. So, and I know what is posterior. So this is my posterior distribution, right? So it is beta 4,8. And what is my estimator? It is posterior mean. So I'm going to take posterior mean. Then it is having value alpha upon alpha plus beta, which is 4 upon 12. So it is 1 by 3, right? That should be the value, right? That is correct. Okay, so I think you can solve this. We have already covered most of things. Fitting distribution is not there, right? Okay, this is the extra part. Okay. So if any doubt is there in solving the problems, maybe you can ask in the next session. Okay, how many sessions are there on week 10? I'm not sure, but what I assume is maybe all of you got the at least idea of what is posterior distribution, what is prior, what is how to find the prior distribution density. What I'm feeling, it's maybe you got it. If you didn't get it, you just again go through the lectures, right, and try to solve some problems. So while solving the problem, do your revision first, right? Do it properly, and then try to solve the problems. Okay, and don't take any help while solving that problem. Just try to solve it by your own. Maybe that will help you not getting wrong answers in the quizzes or maybe in any exam. Okay?
Sure, sir.
Right? Okay. So then shall we stop the session?
Thank you, sir. Thank you for the session. It was wonderful.
Oh,
thank you, sir.
Thank you, guys. Thank you, guys, for joining. Yeah, thank you for joining. So, good night. Bye bye. Bye.
Yes, good night.